Hello and welcome to the Vector virtual session on AUTOSAR Adaptive. I'm Mirko Tischer, and here at Vector in Solution Management I'm responsible for Adaptive Microsar. In the next few minutes or so I will explain to you why there will be more and more software in the vehicle and what AUTOSAR Adaptive has to do with it. You will learn about mechanisms that enable the flexibility of the adaptive platform itself. Finally, I will show you what a framework could look like so that OEMs and suppliers can build new flexible applications. In this session, we look at why software plays an increasingly important role in the automotive sector and what that means for new vehicle architectures. So let's first look at the current trend topics. And here we see three different main topics. We have mobility concepts. We experience nowadays the rise of new mobility concepts with changing customer behavior. We see more car sharing, ride sharing, and upcoming mobility services. And we also see things like vehicle subscription services, where you may order software in your vehicle. They are coming to reality and they are available at selected locations right now. The next automotive trend is electrification. In order to reduce emissions of the vehicles, we have demanding governmental regulations related to emission, and on the other side we have decreasing battery costs. So finally the goal is to increase efficiency while driving with more intelligent vehicle modes like start and stop and sailing. And last but not least, we have the vehicle battery charging topic. So we need more intelligent vehicle-to-grid optimization for situations where many vehicles are returning to their residential neighborhood and all the vehicles start to charge their batteries. So you need an intelligent grid control system in that case. The next topic is automated driving, which is not really autonomous driving, but automated driving. That's enough for us. So it requires handling of different sensor types like camera, sonar, lidar, radar, while taking care of high data throughput. With on and offboard, the on and offboard data have to be combined and evaluated by complex algorithms to, well, get an image of how the surrounding is structured at the moment. So it looks like that these new user experiences are preparing disruptive changes. And the question if this future scenario is mobility as a service, we can't answer that, but we know that it makes sense to focus on core enabling technologies to prepare for those changes. And those enablers are, well, we have three of those enablers here selected. One of those enablers is connectivity. The car is always on. It's connected to the infrastructure, even to the road infrastructure and to other vehicles. Next, we have offboard ecosystems, which are, well, talking to offered cloud services for data collection and for downloading high-resolution map material. And we have also offboard planning scenarios where the road of our vehicle is planned somewhere in the cloud. And last but not least, we have the available high-performance computing resources, which are available in the car nowadays. So in the end, it looks like that those actual automotive trends require much more software in the car. And it's not just about adding much more software, it's also about adding a complete infrastructure from development to deployment. The challenge is now to bridge the gap between a deeply embedded system like a car and the necessary backend structures. There are different scenarios for both ends of the range. We have on one side, we have a safe and secure system developed according to ISO 26262, which is following an embedded integration and debugging process. We have an established automotive supply chain, and we have already established automotive communication protocols and diagnostics. On the other side, this embedded system has to be connected to backends, which are characterized by their support of high performance processors, which require a high bandwidth. They use more or less service-based architectures, and the development process is more oriented towards an open source, agile development approach. These backend systems are requiring dynamic and updatable platforms, which are always connected to the internet. So in the end, the combination makes the difference, and there's one bridging element which is located in those onboard supercomputers. These onboard supercomputers are offering their computing power for head unit and infotainment, but not only. There may be even other functionality located there, merged and consolidate other elements. Additionally, these supercomputers deliver the necessary processing power for automated driving applications. The high-performance ECUs are more and more mastered by the OEM. So the OEM needs the ability to put new software on these ECUs. And this, by the way, requires much more software expertise at the OEM in the future. I have to emphasize that classic AUTOSAR will still be in the vehicle and is responsible for controlling or giving access to intelligent sensors and actuators to provide basic functions in our vehicle and to deliver a fallback computing resource in case that our high-performance computing units or in case there's something wrong with our high-performance computing units. If we compare both systems on a higher level, we see that while we have monolithic binaries with static connections on the classic side, we have standalone executables being connected at runtime on the adaptive side. The development is strictly model-based in both worlds, but on the adaptive side we have a very heavy usage of libraries. And while the configuration is mostly done in code for classic, we use configuration files which are evaluated at runtime and are determining the behavior of adaptive applications here in adaptive. For software that runs on a high-performance computer, the aspect of a good software design and reuse is higher valued than a small memory footprint. And the application software itself is also developed by computer scientists and not really by embedded experts anymore. These facts speak for the usage of AUTOSAR Adaptive. And in the end, when flexibility is required, adaptive may also be the right choice even for smaller ECUs. So in the end, future vehicle architectures will integrate different platforms in the same vehicle. Besides the AUTOSAR Classic platform, we already find commercial off-the-shelf in-vehicle IVI systems. For high-performance clusters in the car, the Classic platform will be complemented by the Adaptive platform. An example of an architecture could look like this. We have the green boxes here providing actuators and sensors. They use signal-oriented communication via the well-established automotive communication protocols, and they run basically on an AUTOSAR Classic platform. Then we have the integration the integration ECUs. They communicate signal and service oriented, and they make some, well, more higher level service and sensor and actuator functions, and they aggregate what is delivered by the mechatronic ECUs and provide it to the vehicle's brain. This is a red box here, which is mainly not just one red box, but probably a few high performance computers located in the vehicle based on a quite complex system on chip. And the software there is more secure like software, but it is developed according to ISO 26262. And this is where we find the focus of innovation in modern vehicles. We have many software contributors providing software there for those kind of systems, and these systems strictly communicate in a service-oriented way. And this is where we in the future find adaptive AUTOSAR. Well, let's have a look at some of the basics of AUTOSAR Adaptive. We first look at the logical architecture, and then we talk about what things make dynamic in our system. So all applications run on top of the AUTOSAR runtime. Its name is ARA, and use the interfaces which are provided by the underlying functional clusters. These the functional clusters belong either to the platform foundation here or to the platform services, and they provide functionality like what the execution management gives us to load and launch applications, in combination with the state management, which is another functional cluster functionality. We may also see functionalities like persistency, which gives us the possibility to load and store application-related data. Applications are programmed in C++ now and may therefore use all the object-oriented paradigms. An operating system interface is available, which gives us access to a POSIX API, which is restricted to a subset of POSIX for adaptive applications. It's a minimum of approximately 280 API functions which may be used from our application. So, and then we have the possibility also to use the C++ standard template library from our applications. An important topic to make systems more flexible is the integrated support of an update concept. Please note that OTA is just an example that OTA update is available in parallel to updating things via diagnostics in the workshop. So we have, if we think about the software installation procedure, then we have an UCM module which is responsible for the complete installing, updating and removing procedures for software. If we receive new software packages from a backend, here are the software packages, and the OTA server establishes first of all a connection to our OTA client. Then the OTA client triggers a software installation at the UCM, which is here at point 2, and then the UCM takes care of installing this new application packages in the system. And this way, so a new application comes into life into that system. Then we may also update those installed applications, and there's not really any project-specific functionality behind that. The update and configuration functionality is already shipped with Adaptive. We may also remove applications as well. So what else makes things dynamic? So the next is service discovery. The question is how to find the correct communication partner in our system. So we use a system where we have service providers offering services in the system, and we have service consumers which need or want to use those services. They find at runtime via a service discovery. And the client, after discovery, the client can now call methods offered by this service, or it can subscribe to events. Note that we are talking about a planned dynamic in this case. The OEM has already designed and tested exactly that connected service. In order to make this work, the AUTOSAR Adaptive Platform comes with a dedicated abstraction of the service-oriented communication. The so-called communication management, or ARA-COM, handles all these aspects locally and remotely. Let's have a look at some more details. The client doesn't need to know where a service is located. It just uses the discovery mechanism, and depending on your service scenario, we can use different levels of flexibility. Starting with the fully static services, where the discovery phase is skipped, to a completely dynamic service discovery. And we can even establish these connections at any point during runtime. Note that there are different network bindings possible for a service, like some IP or DDS, which is data distribution service, IPC, or other custom specific bindings, or even signal-based bindings are possible. In the next few slides, we will have a look onto the impact of the added flexibility for automotive systems. Let's have a look at this small application example realized with the classic approach. We have a rear camera directly connected to our park assist ECU. The park assist again is connected to our display. Steering angle and park assist activation are transferred via a CAN message. The system is completely fixed and the camera is exclusively used for this application. There's no chance to reuse the camera image for any other purpose. This changes with Adaptive. So now we have the same system realized with Adaptive. We again have the camera in the rear. We have a display displaying the camera image. All our ECUs are now connected via a switched Ethernet backbone. Our park assist functionality is now an adaptive application being executed on an application server ECU, and the functionality is wired logically by means of services. Now we may decide to add a new car unlock functionality. The driver is recognized via the camera and the vehicle is unlocked. In this scenario, we just place or install a new software on this application server after start of production, and the new application uses the already available sensors and actuators in that system. To support this kind of flexibility, the software in our application server could look like this. We have on the hardware provided by the Tier 1, we run a POSIX operating system, which is started by a low-level bootloader. In the context of the OS, the necessary platform processes are executed, providing us the functionality of the AUTOSAR runtime. This ARA environment is completed by OEM or Tier 1 specific applications here, tailored to the machine environment. Here we would probably find our camera application. This combination forms a runtime where adaptive applications created by the OEM and Tier 1 or any third party may be deployed. This is the end of the brief introduction to AUTOSAR Adaptive. I hope you could take some impulses with you, and now you know why there is an AUTOSAR Adaptive Platform and what challenges should be overcome with it. We looked at the properties that contribute to the flexibility of AUTOSAR Adaptive. First and foremost, there's the platform's ability to update, which is complemented by the use of service-oriented communication. And we also took a look at the components of the platform implementation. With their help, OEMs and suppliers can implement control units based on the adaptive platform. In our live QA session, you can ask your questions, and I will try to answer them. See you soon.